Hello again. My name is Bashir Hamid, and I'm joined by my teammates Sumit Sharma, Devyani Basta, and Monica Chimedza. Our project is the design of an autonomous underwater vehicle for the RoboSub competition. Our main motivation is the RoboSub competition. This is a competition where assigned tasks mimic real-world applications of AUVs such as underwater exploration and navigation. Tasks could range from entering an underwater gate, object detection with cameras, as well as interacting with those objects and following a specified path. The AUV will be designed to attempt these competition tasks, and it is also desirable for us to have bio-inspired features because we believe it will improve its maneuverability. This is also a valuable opportunity for the team to gain experience in AUV development and improve project management skills. The preliminary sizing of the AUV is achieved by simplifying it as a rectangular block with simple dimensions. In addition, the AUV considered will have three actuated degrees of freedom in the heave, surge, and yaw directions. The intention is to balance the roll and pitch axes by manipulating the weight distribution of the AUV. In the heave direction, the forces acting on the AUV are determined to be the buoyancy force and the weight of the AUV. The lift force generated by the lateral fins is considered insignificant when compared to the buoyant force. To satisfy the competition buoyancy requirements, the force balance in the heave direction is used to determine the volume of material required for the AUV to be positively buoyant by 10% of its mass when it is inactive. The estimated mass is about 21 kilograms. This is governed by the size constraint from the competition guidelines. The minimum downward thrust force required to dive and maintain a depth is then obtained from the difference between the AUV weight and the acting buoyant force. The thruster selected must be able to provide at least 20.5 newtons of downward thrust. Moving on to the surge direction, or the direction of forward and backward motion. Analysis of this direction is important to determine the required thrust force to maintain the desired speed. The main forces acting in this degree of freedom are the propulsion forces from the thrusters and the drag force acting on the body of the AUV. The drag force is estimated using the rectangular form with cross-sectional area obtained from the width and thickness of the dimension selected. The drag coefficient is consistent with that of a rectangle with length L parallel to the flow and T such that the ratio of L to T is greater than 3. The Reynolds number obtained for the criteria is also calculated to be in the same order of magnitude so that the models can be correlated.
For the yaw control, it was assumed that the drag and the lift forces acting on the vertical tail fin would induce a moment around the AUV that would rotate it with an angle delta. From the free body diagram, it can be seen that the angle of rotation of the fin is denoted using theta, whereas the angle of rotation of the AUV about the yaw axis is denoted using delta. From the moment summation about the AUV center of gravity, that is point O, a second order nonlinear differential equation was derived to relate theta, that is the fin rotation angle, and delta, that is the AUV rotation angle. The aim of this exercise was to understand how fin angle and its dimension affects the AUV's overall rotation about the yaw axis. The second order differential equation was solved using two initial conditions, that is, the initial AUV rotation angle delta and its initial angular velocity were assumed to be 0. The fin angle rotation was limited to a maximum of 60 degrees, and the time taken for the AUV to rotate 90 degrees about the yaw axis was calculated. If the AUV was traveling with a constant velocity of 0.9 meters per second, and if the fin angle theta was aligned at 60 degrees, then the AUV would take about 0.75 seconds to make a 90 degrees turn about the yaw axis, as can be seen from the figure here. Using the results from the three free body diagrams in the previous section, the AUV and its fins are sized as follows. This is the top view of the AUV. Its length is about 0.5 meters, its width is about 0.3 meters, and these are the dimensions for the tail fin, as can be seen here. For the pitch and the roll stability, the AUV's center of gravity was strategically placed symmetrically about the X and Y axes. So this is the side view of the AUV after the preliminary sizing. As you can see, the thickness came around 0.15 meters, and these are the dimensions for the lateral fins, which are basically fixed and they're to the front here, and they provide lateral stability. For the calculations in the preliminary sizing, the maximum velocity of AUV was assumed to be 0.9 meters per second, and the mass of AUV was estimated to be 21 kilograms. The team decided to follow a three-step procedure to size the AUV and its fin. The first step is to simplify the AUV as a cuboid and its fin as airfoils to derive a mathematical model and perform preliminary sizing. The second step is to build a 3D model based off the preliminary dimensions and perform a CFD study to determine the lift and drag coefficient for our complicated guitar fish design. The result from the CFD would then be used to resize the AUV and its fins, and a CAD model would be updated in the step 3. The team has already performed the first step and is working on finishing the step 2 to report the final dimensions in the design report 3. After preliminary sizing, here is the CAD model for the guitar fish design that is being used to run a CFD study on it.
Hello there, my name is Davyani and I'm going to be talking about the work plan for the AUV Design Capstone project. On screen you can see a screenshot from the overall detailed Gantt chart we have for the Term 7 and Term 8 academic semesters. Although initially we did mention about using Microsoft Teams as our team grew with recruitment of junior students starting fall. Unfortunately, Teams is not available for month students, and hence our plan moving forward is to use Slack for communication and Microsoft Planner for subtasks tracking among each team member. And next I'll be talking about some of our major project milestones. One major milestone for Term 7 was to have a preliminary CAD design ready for testing and simulation. However, due to our recent change in approach for design of the CAD model that is using the FBDs as initially mentioned by my colleagues in the earlier presentation, we do anticipate a delay in the initially laid out timeline. However, we are hoping to curb this with the onboarding of some juniors, which would help us stay focused on the design aspect and help the project stay on track, so that when we come back in academic 8th semester, we will still be able to complete and achieve the milestones as we had initially planned out in the previous presentation, and that is to have fabrication assembly initiated in Term 8.
Thank you, Davyani. Hi everyone, my name is Mordecai and I'm going to be speaking on the budget and the conclusion for the presentation. For our budget, we were allocated a minimum amount of $500, where the engineering department would provide half the amount, $250, while we as students would be required to provide a minimum of $250 again. We also have other potential sources of funding, which include MUN Student Life, the MUN Design Space, and also potential company sponsors. For our budget, we based our component list on previous technical reports from the competition, and we drew up a preliminary component list. This is the preliminary component list. You can see the components on the left. We wrote down the estimated cost in Canadian dollars, and the grand total came to about $2,670. We believe that even though this is higher than the budgeted amount of $500, we are positive that we'll be able to raise up the funds that are needed based on our conversations with members of the university. In conclusion, we see this as a huge opportunity for student collaboration and for the school to showcase its competency, and we have actually been able to acquire mentorship from Kraken Robotics, who have agreed to meet with us at least once a month, which bodes well for our future sponsorship searches. These are our references. And with that, we'd like to conclude our presentation. Thank you, and we will field any questions you may have.